Okay. So operations with radical expressions basically means do math expressions. Now, you don't have to keep it to radical expressions necessarily. You could go ahead and change them to rational exponents because we know that we can switch between those two things. I'm going to go ahead and get attendance taken care of because I have not yet done that. Here, let me see Diedrich today. Nope. Nope. Maddie's here. Arden's here. Husband's here. Jack. No. Nope. Ben? No. Okay. Cool. All right. You got your book? All right. David? 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 You have your book? All right. Page 333. Page 333. Triple threes. Here we go. We're going to start off with some properties of radicals. Now, here's the nice thing about a lot of these properties of radicals is they work a lot like properties of exponents, which we've been using already. So the properties of properties used to simplify radicals involving square roots can be extended to radical expressions using nth roots. So the square root rules also work for cube roots and fourth roots and fifth roots, etc. That's what that's saying. So for any property of radicals, the product property, for any real numbers a, b, and any integer n greater than 1. So basically, we're talking about the index being greater than 1. So that would be an index of 2, which is a square root, or an index of 3, which is a cube root. And we're talking about integers as well. So we're talking about greater than 1, positive whole numbers greater than 1. So 2, 3, 4, 5, and so forth. The nth root of a times b is equal to the nth root of a times the nth root of b. So that basically just means you're allowed to separate out that multiplication underneath the radical into two radicals multiplied together. And it says if n is even and a and b are both greater than 0, or if n is odd. Now, if n is even, a and b both need to be greater than 0. Why? Goes back to this right here, real numbers. If a and b are negative and the index is even, do we get real numbers? No, we get imaginary values. If you square root or fourth root or sixth root a negative number, you get I, which is not a real number. So we're talking about real numbers only here. And if n is odd, it doesn't matter if a is positive or b is positive or negative. They could be negative because cube rooting a negative is a negative number, and that's okay. So, for example, the square root of 12 times the square root of 3 is equal to the square root of 36, which is equal to 6. Because 12 times 3 is 36, so you can combine those or you can separate them out. The cube root of 4 times the cube root of 16, multiply 4 and 16 gives you the cube root of 64, which is equal to 4, because 4 times 4 times 4 is 64. It also works for quotients. For any real numbers a and b is not equal to 0. Take a look at this fraction here. Why can b not equal to 0? Yeah, you can't divide by 0. Dividing by 0 isn't a thing. If you have something, remember that division is taking something and splitting it into this many groups, right? That's what division is. If you have 4 things and you split it into 2 groups, you have 2 groups of 2. If you have 4 things and you try to split it into 0 groups, you can't take something and split it into no groups. That doesn't make sense. So mathematically, you can't divide by 0. So the denominator b, whatever the denominator is, can't be. Any integer n greater than 1. So again, the index has to be a positive whole number more than 1, square root, cube root, etc. Our examples here are telling us that if you have something like the square root of x to the 4th divided by 25, you can break apart into 2 separate square roots. The square root of x to the 4th on the numerator divided by the square root of 25 on the denominator. The square root of x to the 4th is x squared. The square root of 25 is 5. So you could have x squared over 5. Or you could write it as 1/5 times x squared. And the reason for that is x squared is the same thing as 1x squared. And 1 over 5 is the same thing as 1/5 multiplied by x squared. So 1x squared over 5 is the same thing as 1/5 x squared. So it's just saying that those two things are equivalent. The other example here, the cube root of 27/8. If you break this apart, you can have the cube root of 27 divided by the cube root of 8. Cube root of 27 is 3, cube root of 8 is 2, so it's 3/2 or 1.5. So those are the basics. Our key concept here says the simplest form of radical expressions, but let's say the properties of radicals and processes of rationalizing the denominator. We've already been doing that, by the way. Can be used to write radical expressions in simplest form. So this is actually going to be, we're on page 333. The process for simplifying these is basically the processes we had, the same processes we had the other day when we were talking about radical expressions and rational exponents. There's really no difference in terms of the simplification process. So the index is as small as possible, meaning if you can square root something, square root it. If you can cube root something, cube root it. The radicand, something under the radical symbol, contains no factors other than one that are nth root powers of the integer or the polynomial. Now, basically what that means is if you can factor out a perfect square or a perfect cube or a perfect fourth from that radicand, depending on the index, then you should do that. The radicand contains no fractions. So this, the radicand, x to the fourth over 25 contains a fraction. This is not considered to be simplified. This would be simplified. So the thing under the square root or the cube root or the fourth root cannot have a fraction in it. And you cannot have radicals in the denominator. So even when you split apart the radicand into two separate radicals, the denominator cannot remain a radical in your final answer, which this one didn't, and neither did this one over here. So let's start working. These first couple examples are going to walk us very carefully through this process. So this one says the cube root of negative 27, a to the 6, b to the 14. So if we're factoring this into perfect cubes is what's happening here. Negative 27 is a perfect cube. What is negative 27 the perfect cube of? Positive or negative? Negative, yeah. Negative 3. A to the 6th is the perfect cube of what? A squared, yeah. Remember back from, what was it, earlier this week, if this number is divisible by that one, then you can write it as a perfect nth value. So 6 divided by 3 is 2, therefore a squared to the third power is equal to a to the 6th. Now, b to the 14. 14 is not divisible by 3. So what you're going to try to do here, this is where things get a little bit different. We have not yet done this skill yet, but what is the largest number that is less than 14 that is divisible by 3? 12, exactly. So a to the 12th, 12 divided by 3 is what? 4. So this would be a to the 4th cubed, which is a to the 12th, or not a, b, sorry, saying the wrong variable here. B to the 4th cubed, 4 times 3 is 12, times another b squared would get us back to this b to the 14th. So negative 27 is a perfect cube. A squared is a perfect cube. B to the 14th is not a perfect cube, but it has a perfect cube factor, and the perfect cube factor is b to the 12th, which factors to, or not factors, but reduces the b to the 4th to the third power with a leftover of b squared. Everybody good so far with that? Okay. Then it's just breaking, it's basically doing the exact same thing, writing it here and here, except it's basically splitting apart everything into its own radical. So instead of having one combined radical, it's saying the cube root of negative 3 cubed times the cube root of a squared cubed times the cube root of b to the 4th cubed times the cube root of b squared. The first three here, exponent of 3 cancels out with index of 3. Exponent of 3 cancels with index of 3. Exponent of 3 cancels with index of 3. Exponent of 2 does not cancel with index of 3 because those are not inverse operations. So this is going to stay the same. All of these 3's will cancel. You get b to the 4th. 3's will cancel. You get a squared. 3's will cancel, and you get -3. So -3a squared b to the 4th times the cube root of b squared. That is the simplified result there. If you take a look, if you go back to the rules for something being simplified, the index value n is as small as possible. Yeah, we reduced n from 3 to 1 on all 3 of those. The index of 3 turned into an index of 1. This one couldn't be reduced any further, so it's as small as it can get. 3 is going to be the smallest index there. The radicand contains no factors, or fractions. Sorry, radicand contains no factors other than the one that are powers of the integer or polynomial. That's true. There are no fractions, there are no denominators, so we're all set there. We never had any to begin with on that one. Number 1, part B. So this one says we've got the square root of 75x to the 12th y to the 7th. 75 is not a perfect square. It does have a perfect square factor. And it's kind of making things a little bit easy for you here because it's saying, hey, if you divide 75 by 3, the leftover is a perfect square factor. What's 75 divided by 3? 25. So 25 is the largest perfect square factor of 75. It's also telling us that x to the 12th is a perfect square, and that's because 12 divided by 2. 12 divided by 2 is 6, so that's x to the 6th squared. Y to the 7th power is not a perfect square because 7 doesn't divide by 2. However, the largest factor of y to the 7th that is divisible by 2 is y to the 6th. It's just one less factor than 7. So that would be y to the 6 times y. 6 divided by 2, index is 2. 6 divided by 2 is 3, so that's y cubed squared, which is y to the 6th, with the extra y there, which would bring us back to y to the 7th. Any questions about this so far? We're just looking at each individual term, or each individual part of the term underneath the radicand, and then just kind of breaking them apart into their individual pieces. Then we can write these all as separate radicals. And so we got the square root of 25, which is the square root of 5 squared, multiplied by the square root of 3, don't forget about that, multiplied by the square root of x to the 6th squared, multiplied by the square root of y to the 3rd squared, and multiplied by the square root of y. 3 of these things are perfect squares, 2 of them are not. 5 squared, square root of 5 squared is a perfect square. It equals what? 5. All right, so 5 goes here. X to the 6th squared is a perfect square of x to the 6th. So that square roots to x to the 6th. Y cubed squared, square root that, you get y cubed, which leaves us with what in our radicand? What 2 things are not perfect squares here? 3 and y. So under the radicand, we get 3y. And that is our answer. Deliveries from this morning. Nice. All right. Here's the bag. Probably you on your own for a couple minutes. By the way, you don't have to write out all the steps. Like if you can combine some of them, if you know some things are going to be perfect squares, you don't have to write them out in that detailed format that you saw on the last page. So just as a heads up on that. We'll definitely be finishing this lesson on Monday as well. Also, before I forget, we only have 2 more sections, I believe, in this chapter. Lesson, no, let's see, 5 and 6. Are there 7? No, there's 6. Okay, we have 2 more lessons. Lesson 5 today and Monday. Lesson 6 will be on Tuesday. So expect your first test to be at the end of next week, either Thursday or Friday of next week. That's when your test is going to be, depending on how much time we spend on the lessons, but your test will be next Thursday or Friday. All right. So, first question here. Hudson, is 4 a perfect fourth? No. Okay. So 4 is not a perfect fourth, which means that this number, there's nothing we can do to simplify that 4 underneath the radical. Maddie, is 5 a perfect fourth by itself? No. Does it have a perfect fourth factor? Yeah. What is the perfect fourth factor of x to the 5th? X to the 4th. Good. Which means we're going to have a leftover x. Jaden, is y to the 20th a perfect fourth? Yeah, because 20 divided by 4 is 5. All right. So this is going to be equal to the 4th root of 4 times the 4th root of x to the 4th times the 4th root of x times the 4th root of y to the 20th. And I'm just going to combine a few steps, like I said, because they, and I appreciate it, but the first couple examples always go a little bit overboard in terms of detail, which is good, so you can see exactly what's happening. But when you do these yourself, you're welcome to just do, like, you know, a couple of steps, combine a few steps, things like that. So anything that is a perfect fourth needs to go in front of the radical in the final answer. Because this is not a perfect fourth, this will not start our final answer. This one is a perfect fourth, so it will start our final answer. What is the 4th root of x to the 4th? X. 4th root of x is also not a perfect fourth, therefore this will not go next, because the 4th root of y to the 20th is a perfect fourth. Jasleen, what is the 4th root of y to the 20th? Y to the 5th. Good. So we're going to have x, y to the 5th times the 4th root of 4x. And that's it. All right. For B, Ben, is 60 a perfect square? No. Okay. So there is no number that multiplies by itself to equal 60. Does 60 have a factor that is a perfect square? Yeah. What is the largest perfect square factor of 60? It's probably smaller than you might expect. What are perfect squares that are less than 60? 49. 49. 60 isn't divisible by 49. 36. Is 60 divisible by 36? No. 25? No. 16? No. 9? No. 4? Yeah. So it's kind of weird because 4 is the largest perfect square factor of 60. You'd think it might be a little bit bigger. It's not. What is 60 divided by 4? 15. Okay. So 60 divided by 4 is 15. I'm just going to write some stuff above this because the hole punch is going to get in the way. So this is going to be the square root of 4 times the square root of 15. A cubed. Arden, is a cubed a perfect square? No? Okay. Does it have a perfect square factor? A squared, right? Yeah. So a squared is a perfect factor of a cubed. So we're going to write times the square root of a squared. Jesus, a squared times what equals a cubed? Think about it for a second. You can do it. What plus 2 equals 3? What plus 2 equals 3? Yeah, 1. Okay. So a squared times a to the first power, which is just a. So a times a squared is a to the third. All right. David, is 22 divisible by 2? Yeah. All right. So then a to the 22nd is a perfect square. So multiplied by the square, not b, not a, b. B to the 22nd is a perfect square. So perfect squares here. 4, a squared, b to the 22nd. Those are all perfect squares. So if you square root 4, Francisco, what's the square root of 4? What's the square root of 4? 2. Okay. Who have I not talked to today? Alexia, what's the square root of a squared? A to the first power, yeah, a. Okay. Emmanuel, what's the square root of b to the 22nd? B to the 11th, good. So just divide by the index, right? 2 divided by 2 is 1, a to the first. 22 divided by 2 is 11, b to the 11th. 2 times 2 is 4, square root of 4 is 2. The two things here that are not perfect squares are 15 and a. So square root of 15a. So 2ab to the 11th times the square root of 15a. All right. Okay, so far? Isn't too bad, is it? All right, let's keep going. Example 2. We're using the quotient property this time. So we're going to simplify each expression. The first thing it tells us to do is to go ahead and split apart the numerator and the denominator into their own radicals. So we're just going to write 24 a to the 6th on the numerator and 125 on the denominator. We're just breaking apart that quotient into two separate radicals, the quotient of two radicals. All right. 24 is not a perfect cube. 24 has a perfect cube factor. And it tells us what the perfect cube factor is right here. So what number goes here? 3. 2 cubed is 8. So 8 is a perfect cube factor of 24. 24 divided by 8 is 3. 8 to the 6th is a perfect cube because 6 divided by 3 is 2. So that would be the cube of a squared cube. On the denominator, 125 is a perfect cube. It's the perfect cube of 5 cubed. So turns into that. Then it's going to use the product property on the numerator to split apart every item, every part of that term on the numerator and turn it into multiplication of radicals. So the cube root of 2 cubed times the cube root of 3 times the cube root of a squared cubed divided by the cube root of 5 cubed. 3 of those 4 radicals are perfect cubes. 1 of them is not. So the cube root of 2 cubed is 2. The cube root of a squared cubed is a squared. And the cube root of 5 cubed is 5. You get 2a squared times the cube root of 3 over 5. All right. Go to the next one. If there's questions, let me know. Stop me at any moment if you need to ask a question. Otherwise, we'll keep going. Okay, 4th roots this time. Break it apart into the quotient of 2 radicals. On the numerator, we do have a perfect 4th factor of 80, even though 80 itself is not a perfect 4th. What's 2 to the 4th power equal? 16, yeah. So the perfect 4th factor of 80 is 16. 16 times 5 is 80, so that's where the times 5 comes from. Y to the 14. That is not a perfect fourth because 14 is not divisible by 4, but the largest value that is smaller than 14 that is a factor of 4 is 12. So if you take 2 away from that, y squared over here, this is y to the 12th, which turns into y cubed to the 4th. And then we can put on the denominator. Is 256 a perfect fourth of 16? Okay. So we could write 16 to the 4th power? That seems a little large. Maybe it's 4 to the 4th. I think it's 4 to the 4th. 4 to the 4th. Okay. Yeah. 4 to the 4th power. Okay. And then z to the 4th would be a perfect fourth as well. We can just put z in parentheses and put it to the 4th power like that. Or you can just write z to the 4th again. Doesn't really matter. Okay. So then if we separate out all our radicals on the numerator and denominator using the product property of radicals, that'll do that job there. Now, let's take a look here. This is the first time we've seen absolute value. We still have to consider absolute value because if you simplify a radical that has an even index and your exponent after simplifying that even index radical is an odd exponent, which is y cubed, we need to guarantee that the result is positive because we're talking about, there is no plus or minus out here, there's no negative either, which means we're talking about the principal roots, which means we need to consider that this needs to remain positive. The only way to guarantee that something cubed is positive is if you take the absolute value of that. So that is still part of these problems if you need to. So keep that in mind. And then we've got 5y squared underneath our 4th root here. On the denominator, what's the 4th root of 4 to the 4th power? 4. What is the 4th root of z to the 4th? Z. What happened between here and here? How did we get from here to here? What's different? There's no 2. Anything change on the denominator? Yeah, the 4 reduced to a 2. So basically we're saying, all right, 2 divided by 4 is 2. Or I guess 2/4 reduces to 1/2 would be the better way of saying that because the fraction that we're dealing with there. So you can still simplify coefficient values, regular numbers, as long as the regular numbers are multiplied and they're out front, outside of the radical. So those can go ahead and simplify. Okay, let's try the next one. And I think we might have time for this check here and then the next example, and then we'll probably call it a day. And then we'll finish this up on Monday. So I'll also give you the assignment in case you want to get a head start on it as well. It will not be due on Monday though, because we're not even done with the lesson. So writing this in simplified form, we can do multiple things at the same time. That is okay. So is 9 a perfect square? Yes. All right. So on the numerator, I'm going to write the square root of 9. Is 8 x to the 8th a perfect square? Think about this number and the index. What's the index of a square root? What's the index? 2. Does 8 divide by 2? Yeah, so x to the 8th is a perfect square. So times the square root of x to the 8th. Is y to the 13th a perfect square? Does 13 divide evenly by 2? No. What number smaller than 13 divides evenly by 2? 12. So times the square root of y to the 12th times the square root of y. We have to break that apart. Y to the 12th times y is y to the 13th. That part is a perfect square. That part is not. 9 is a perfect square. X to the 8th is a perfect square. On the denominator, is 25 a perfect square? Yeah, so we can keep that as the square root of 25. Is x squared a perfect square? Yeah, because 2 divided by 2. So everything here is a perfect square except for the square root of y on the numerator. So that means everything under a radical is not going to be under a radical in our answer. So what is the square root of 9? 3. What is the square root of x to the 8th? X to the 4th. What's the square root of y to the 12th? Y to the 6th times the square root of y over, what's the square root of 25? What is the square root of x squared? Is that our answer? Not quite. If we could simplify 3/5, we would. It doesn't. However, x to the 4th over x does simplify because we still need to consider our rules of exponents. And when you have the same base value, what do you do with the exponents when there's a quotient? Subtract them, yeah. We dealt with that with our rational exponents earlier this week. 4 minus 1 is what? 3. So the denominator of x cancels out. The 4 on the numerator for the exponent becomes a 3. So the answer to this one is going to be 3x cubed y to the 6th times the square root of y over 5. Questions about that one? I don't know exactly why, but simplifying radicals is one of my favorite things to do with algebra. I'm weird like that. Any questions on this before we look at we'll just do one more example and then we'll call it a day. Also, I'm going to print something off for you before the end of class today as well. That will help you out figuring out perfect nths of numbers. So let's look at the next thing here. Adding and subtracting radical expressions. Radicals can be added, or we haven't done that yet. We've only done multiplying and dividing. Now we get to talk about adding and subtracting. So radicals can be added and subtracted in the same manner as monomials. Basically what that means is, in order to add or subtract algebraic expressions, you need like terms, right? Everybody remember combining like terms? That's basically what we're doing with radicals as well. It says in order to add or subtract, the radicals must be like terms. There it is. Radicals are like radical expressions if both the index, square root, cube root, fourth root, etc., and the radicand are the same. So both the radical symbol needs to have the same index and the thing underneath the radical symbol needs to be the same as well in order to be able to combine them using adding or subtracting. So if you have there's examples here. Although two radicals, such as the square root of 18 and the square root of 32, may not appear to be like radicals, because even though they're both square roots, the radicands are not the same. 18 and 32, obviously not the same number. If you simplify each radical, you can see that the square root of 18 is equal to 3 times the square root of 2, because the square root of 18 has a perfect square factor. The perfect square factor of 18 is 9. The square root of 9 is 3, with a leftover of root 2. And the square root of 32 has a perfect square factor of 16. 16 times 2 is 32. The square root of 16 is 4. So you get 4 times the square root of 2. That means that these are like radicals because we have the same index, square root, and we have the same radicand, 2. If you were to add them together, you would add the two coefficients. 3 plus 4. 3 plus 4 is 7. So this would equal, so go ahead and write this down. 3 root 2 plus 4 root 2 equals 7 root 2. We're basically treating the square root of 2 as a variable. It's like 3x plus 4x equals 7x. It's the same idea. So if your index and your radicand are the same, you can add the coefficients together, keep the same index and radicand, combine it just like you would a number attached to a variable. No difference. All right. Radicals with the same index can be multiplied using the product property of radicals. If the radicals have coefficients before the radical symbol, multiply the coefficients. Then multiply the radicands in each expression. To multiply radical expressions with more than one term, you use the distributive property or FOIL. So, for example, on this problem here, if you have the cube root of 6 plus 1 times the cube root of 2 minus the cube root of 7, you would have to use FOIL, first, outer, inner, last. So if you multiply the first two terms together, the cube root of 6 times the cube root of 2 is equal to the cube root of 12. Because 6 times 2 is 12, and you keep the index the same. And then outer, the cube root of 6 times the negative cube root of 7. 6 times 7 is 42. Positive times negative is negative, so it's the negative cube root of 42, or minus the cube root of 42. Inner, 1 times the cube root of 2 is the cube root of 2, so plus the cube root of 2. And then the last, 1 times the negative cube root of 7 would be minus the cube root of 7. This is what you'd get if you'd multiply that out. And in looking at this, none of those have perfect cube factors as far as I'm aware. So this would be your answer, because none of them would be like radicals. In fact, we'll go ahead and pause there for today. However, your assignment, if you want to get started on it, we're going to do 1 through 45 odds. And then we'll do, let's see, 47 through 50. 54. And 56. That'll be your assignment. If you want to get started, you're welcome to get started. So far, we only really have the ability to work through 1 through 9 odds. If you want to try to do that, you're welcome to try to do that. I really want to print off something for all of you. I don't know if I'm going to have time before the day is over. I'll definitely get it to you on Monday, though. So I'll just put a reminder for myself for Monday. It'll make your life easier when you're figuring out if things are perfect squares or cubes or fourths and whatnot. So go and get your stuff packed up.